All right, let's dive into one of the most powerful and, for a long time, most secret technologies ever created, the nuclear weapon. We're going to break down the science and the incredible engineering that makes it all possible, starting right down at the atomic level.
You know the story of every single nuclear weapon. From the very first prototypes to the most advanced modern arsenals, it all begins right here, inside the atom. The entire goal is to tap into the fundamental energy that holds the nucleus together and release it all in a literal flash.
So how are we going to tackle this? Well, think of it like we're climbing a complexity ladder of nuclear design. We'll start with the absolute basics of the physics, and then we'll see how engineers took those principles and created more and more sophisticated designs to build ever more powerful weapons.
To get at that incredible atomic power, weapon designers really have two main tools in their toolbox, two different kinds of nuclear reactions they can use.
First up, you've got fission. The easiest way to think about this is atomic splitting. You take a really heavy, kind of unstable nucleus like uranium, you split it apart, and boom, it releases a massive amount of energy. And then you have the total opposite, fusion. This is where you take super light nuclei, like different types of hydrogen, and you slam them together so hard they fuse into one. This is literally what powers our sun, and it releases even more energy than fission. Now, both reactions are incredibly important, but everything really gets started with fission. The big puzzle for the first designers was figuring out how to make one single tiny atomic split trigger billions and billions more almost instantaneously.
And the secret ingredient for that is something called a fissile material. You see, not all nuclear fuel is the same. What makes stuff like uranium-235 and plutonium-239 so incredibly special is that their atoms can be split by a neutron, no matter how much energy that neutron has. That property makes them absolutely perfect for creating a reaction that can sustain itself.
And that self-sustaining process? That's the famous chain reaction. The best analogy is lighting a single match. That one match lights two more, and those two each light two more, and on it goes. In a split second, you go from one tiny flame to an uncontrollable inferno. That's the exact principle behind a fission bomb.
Now, take a look at this, because it really shows you how it works. A single neutron hits a U-235 atom, it splits, and it releases energy plus, on average, a couple more neutrons. Those then go on to hit other U-235 atoms. But here's the catch. It's not a perfect system. Some of those new neutrons might just fly right out of the material and not hit anything. Or they might get soaked up by a non-fissile atom like U-238, which stops the reaction cold for that neutron.
So the whole game is about managing those lost neutrons. To make absolutely sure that each split causes at least one more split, you need a certain amount of this fissile material, and it needs to be packed together at a certain density. That magic threshold is called the critical mass.
And this right here created a massive engineering challenge. How in the world do you assemble a supercritical mass that is more than enough to get the reaction growing so incredibly fast that the bomb doesn't just fizzle and blow itself apart before the real exposure can even get started? Well, the early designers came up with two main solutions.
The first, and by far the simplest approach, is what's called the gun assembly method. And it's pretty much what it sounds like. It's basically a small cannon inside a bomb. You have two separate pieces of uranium, and neither one is big enough to be critical on its own. One is shaped like a bullet, the other is the target. A regular chemical explosive fires that bullet down a barrel, slamming it into the target. For one tiny instant, they combine into a single supercritical mass, the chain reaction takes off, and the weapon detonates. This is the design that was used in the bomb dropped on Hiroshima.
Okay, so that's method one. But method two, well, this is where things get way more complicated and also way more efficient. It's called the implosion design.
Instead of slamming two things together, this design is all about squeezing. You start with a single ball of plutonium, which is subcritical. But surrounding this core, or pit, is a perfectly shaped layer of conventional explosives. When these are detonated with unbelievable precision, we're talking microseconds, they create a perfectly spherical shockwave that crushes the plutonium core inward, massively increasing its density. That compression pushes the atoms so close together that the core instantly becomes supercritical, and the whole thing detonates.
So now we have two ways to start a fission chain reaction. But how do we get from those first bombs to weapons that are thousands of times more powerful? Well, for that, we have to climb a few more rungs on our complexity ladder by adding some new physics into the mix.
The next big leap forward was an idea called boosting. Here's the trick. You put a tiny amount of fusion gas, usually deuterium and tritium, into the hollow center of the plutonium pit.
When the fission reaction kicks off, the heat and pressure are just insane, and it actually triggers a little fusion reaction in that gas. Now, here's the genius part. The fusion itself doesn't add a ton of power. What it does do is release this incredible flood of high-energy neutrons that just pepper the fissioning plutonium, causing way more fission to happen before the bomb tears itself apart. It's basically a supercharger for a fission bomb.
And that idea, using a little bit of fusion, leads us directly to the top of the ladder, the most powerful, the most complex design of all, the staged thermonuclear weapon. You probably know it as the hydrogen bomb.
Okay, you got to appreciate how unbelievably clever this design is. You are essentially using one nuclear bomb to trigger a second, much bigger one. So here's the sequence. First, a fission bomb, called the primary, detonates. It releases a massive, instantaneous flood of X-rays. Those X-rays fill the weapon's casing and blast the outside of the second stage, crushing it inward with unimaginable force. It's called radiation implosion. This compression is so violent it sets off a fissile spark plug in the middle of the secondary stage, and the intense heat and neutrons from that explosion finally ignite the main fusion fuel, unleashing just a catastrophic amount of energy.
Whew, okay, that was a lot. So let's just take a breath and recap the 4 distinct designs we just walked through, this evolving path to incredible destructive power.
And this table just lays it all out for us. It is our complexity ladder in visual form. We start with the simple but kind of wasteful gun assembly type. We move up to the more complex but much more efficient implosion design. Then you add that layer of sophistication with boosting to squeeze out even more power. And finally, you reach the top, the staged thermonuclear design, the most complex and by far the most powerful.
And what's just staggering is that this basic 2-stage design, which was figured out way back in the early 1950s, is still the blueprint. To this day, no one has found a more efficient way to build a thermonuclear weapon. This is the design that every single major nuclear power uses.
I mean, think about that for a second. To go from a simple cannon insider bomb to a multi-stage hydrogen bomb in less than 10 years, it's one of the most incredible and frankly one of the most frightening technological leaps in human history. It really leaves you with a heavy question to ponder. What does this rapid, lethal mastery of physics truly tell us about human ingenuity and about the immense, almost unimaginable responsibility that comes with it?